Hello everyone. Just checking my sound levels, making sure everything's working fine. Looks okay. All right. This evening, what I'm going to do is I'm going to just go over some problems on sound, and for the assignment tomorrow. Well, that's it. Let's begin. Let me just remind you the topics that we went over on sound. One of them was intensity, and there's two ways of expressing intensity. One of them is just plain old I, the intensity defined as you see here in this formula right here. Okay, and it's the amount of energy deposited over a certain amount of area for a certain amount of time. And the other way that intensity is defined or can be expressed is in terms of decibels, and that's a log scale. Okay, and this is the first time we've ever seen a log scale, and so I'll go through this carefully. Some people emailed me about questions 5 and 6 on the assignment. They found them a little bit challenging, and I think it has to do with a combination of the log scale or the decibel scale with the inverse square law. Okay, so we'll that's what these first questions are about. And then the other thing we did with sound was Doppler effect. Okay, and so the last question I'll do this evening is an example of the Doppler effect. Okay, so let's begin. All right, so question number one here. At a distance of 10 meters, a sound source deposits 0.25 milliwatts per meter squared. Okay, how much energy is deposited over an area of 3 by 4 meters in 30 minutes time? Okay, now in this question, that 10 meters doesn't matter. Okay, it does matter because the subsequent question will depend on that number. But for this question, it's just a matter of how much energy is being deposited per unit time. Okay, and it's 0.25 milliwatts of power per meter squared. Now, a milliwatt or a watt is actually a joule per second. So you don't quite see in here the time dependency, but there is. Okay, I want us to get used to watts because when we come to electricity, we'll be talking about power and electricity, and that's measured in watts. And you're probably familiar with watts because if you buy an incandescent light bulb, you know it might be like an 80-watt light bulb. Okay, and so that means that 80 watts means that 80 joules of energy are being used per second. Okay, so let's go ahead and do this problem. And let me, so this is the formula here. It's actually the definition of the intensity. Okay, it's how much energy is deposited per unit area per unit time. Okay, and the intensity I tell you is 0.25 milliwatts per meter squared. Okay, and let me do a couple of conversions there. First of all, milli, that's not MKS. Okay, so let's replace the milli with a thousandth. So 0.25 times 10 to the negative 3, right? A thousandth of a watt. That's what milli means. And meters squared like that. Okay, now the next thing I want to do is also take that watt and express the watt as by definition, a watt is a joule per second, like that. So let's express it that way. Okay, that's equal to this number right here. All right, and joule per meter squared second. Okay, now in this form, I think it's a little bit more obvious how to answer the problem, because what it's basically saying is this many joules is deposited per meter squared of area every second. Okay, and that's exactly what this formula is. Now, how much area do we have? Well, our area, I told you, was a 3 by 4 meter, I don't know, just square area. Okay, and that's basically 12 meters squared of area. All right, so there's the A. The time, delta T, how long is this going to go on for? Well, delta T is going to go on for 30 minutes. Okay, but we don't want it in minutes, we want it in seconds, so it's going to be 30 times 60 seconds. Okay, and that will equal 108, 1,800 seconds, like that. Okay, so there's your delta T, and what we actually want to calculate, we have I. You just align this like that, so we do have I there like that. There's that. And so what we want to calculate is delta E. And I guess you could use this as a formula, although I tend to think of it as just a definition. If you take this here, like that, and you multiply both sides by area times delta T like that, you isolate your delta E, okay? And that's what we're solving for, because I asked in the question, how much energy is deposited, all right, over that area, over that amount of time, okay? And so delta E, just turn the equation around the other way, reads a little bit nicer, is that, and that's going to equal your intensity, which is this number right here, all right, multiplied by the area, which we said was 12 meters squared, okay, multiplied by the time, which is half an hour, which is 1,800 seconds, like that. And let me work that out for you. .4 joules. Okay, there you go. So that's it. And it's really not much deeper than that. It's more or less getting in your mind what the definition of intensity is. Okay. So I think I gave the analogy of like rainfall. When you say how intense is your rainfall, well, how would you determine how intense a rainfall is? You might put a barrel out there, but then measure how much water you capture. But the amount of water you capture is going to depend on a couple of things. One is how big the barrel is, or at least the mouth of the barrel. That's your area right here. Okay, the definition. Let's take a look here. That's the area right there in the definition. And it's also going to depend on how long you wait. Okay. And so you really have to divide those out to, and the amount of water is like your delta E. Okay, you really have to divide them out to be fair, because if you're going to compare the intensity with one barrel collecting over one period of time with another barrel collecting over a different period of time, okay, and you want them to give the same number because it's the same intensity of rainfall, you have to divide out the area of the mouth of the barrel and the time, okay? And this is the analogy is actually quite strong here because it's the same thing, okay? So if you're saying so much energy is being deposited per unit area, per unit time, okay, you want to say, well, how much energy is deposited in total? Well, that'll depend on how much area you've got, okay? You have to multiply by that. So down here, how much energy is deposited, you have to multiply by the area, and you also have to multiply by the time, because more area, more energy, more time, more energy is deposited. Okay, let's go on, okay? Now, in this one, I say, what is the intensity of the same source at 30 meters? Whoops, cut it off a bit there. Okay, at 30 meters. Now, in the previous, up here, remember I said you don't really need the 10 meters at this point, okay? So watch out for that on my assignments or tests, because I've got questions that, they concatenate one after another. I might give you information in one that you say, well, I didn't really need that information there. That's right, you don't need it in maybe that question, but you might need it in a later question. I don't like giving questions with red herrings in them. That is, extraneous information that you'll never use. But that doesn't mean that in any one particular question you'll use all that information, because you might need it for some later question. Okay, so I don't want to say I won't ever give a red herring. I mean, sometimes it makes sense to say, do you really know what information to pick out? But generally speaking, I don't like to trick students. Okay, so at 10 meters we have this intensity. Okay, 0.25 milliwatts per meter squared. What's the intensity going to be at 30 meters? Okay, so 30 meters is 3 times as far. Now, that's actually the inverse R squared law, and it can be written in different ways, but the way I wrote it in our notes is like that, okay? And basically, as you go further from the source, the intensity drops. And it doesn't drop linearly, it actually drops as the radius squared. So if you're at a certain distance and you have some intensity, if you double the distance, you go to 1/4 the intensity. Not a half the intensity, but a quarter. Double, that's like 2. 2 squared is 4. Inverse R squared, so it's 1/4. Okay. If you triple the distance, then you'll go to 1/9. Why 1/9? 1/3 squared, that's 1/9. Okay. In fact, in this problem, we're going to triple the distance. Okay, so we know we're going to go to 1/9. But let's actually use the formula, see how that works out. Okay, and so here we could say, all right, fine. We'll have an intensity I1 of the original intensity up here. Okay, we'll have that intensity there at R1, which is 10 meters. Okay. And we want to calculate what is I2. We don't know that because that's what I'm asking for. At R2, which is 30 meters, like that. Okay. And then it's just a matter of plugging into this formula right here. Okay, so we're going to solve for I2. Let me move that down a bit. We're going to solve for I2. So let me actually just rearrange this formula to start with. So this is I1 divided by I2. So let me multiply both sides by I2. So that'll be this formula again. But now I2 is going to be on this side like this. Whoops, not I3, I2. Okay, and multiplying that fraction there like that. And that's still not it because we want to isolate I2. So let's divide both sides by this. Okay, and dividing by that is like multiplying by its reciprocal. And so we're going to get I1 multiplied by the reciprocal of this. Now what's the reciprocal? Here we have R2 over R1. So we're going to get R1 divided by I2 squared, and that's going to equal I2 like that. Okay, so I hope I didn't go too fast there, but this is like R2 squared, so that it's in the numerator, so on the other side it'll go into the denominator, and here R1 squared is in the denominator, so it becomes the numerator on the other side. Remember, dividing by a fraction is like multiplying by its reciprocal. Okay, so that means that I2 is going to equal, well, I'll just rewrite this like that. Okay, and I1, I give you that number, and R1, that was the 10 meters, but now it's squared, okay, divided by R2, and that's 30 meters squared like that. Okay, and let me work this out. Okay, I'm going to take this unit and put it out here like that. Okay, so the answer is going to come out in milliwatts per meter squared, which isn't NKS, but that's okay. All right. Let me see what that works out to. It works out to this. Let me round off to 3 significant figures. I2 is going to equal that many milliwatts per meter squared. Okay, so I1 was 0.25. Where is it? Right here. All right. And I2 is 1/9 that. Okay, so you could just take this number and divide by 1/9. And you say, where did I get that 1/9 from? How do I know it's 1/9? Well, if you take 10 squared and divide it by 30 squared, that's 1/9. Okay, and that's sort of what I said earlier. You know, the inverse r squared, what it says basically is, you know, if you double the distance, it's 1/4. But if you triple the distance, it's 1 divided by 3 squared, or 1/9. Okay, now this should look kind of like question 5 and 6 on the assignment, but there's a difference. In question 5 and 6, I did not give you intensities as I, the linear unit. Remember, I is the linear unit. I gave them to you in terms of the decibels, which are the log units. And so you say, well, how do I solve that? And I guess it might have been a bit tricky because you kind of have to combine 2 formulas. You have to use this formula for the inverse r squared because you're changing the distance, but you have to use this formula to convert back and forth between beta and I. Okay, you really can't do any kind of arithmetic with beta. All right, and I think I explained this during the lecture, but it's worth explaining again because these are log scales, because your decibels are log scale. If you have one source, which is say 25 decibels, and you have another source which is 75 decibels, like that, it's really tempting to say, oh, well, then you have 100 decibels. No, it just doesn't work like that. Okay, so you should not think of decibels as like units that add. And you go, well, what good are they? Like, what are they good for? Well, I gave, you know, a lot of examples during that, and I won't repeat it. They kind of give you like these brackets. Okay, so if you're in the 25 decibel range, that's a very low, much lower bracket than in the 75. So it allows you to compare intensities over a very large range. But they don't, that's the advantage. It allows you to compare over a very large range. But the disadvantage is that arithmetic doesn't work with them. Okay, and so, yeah, that's not going to work. And so you can't just do something like this. You can't take this formula here and say, oh, instead of I1 and I2, I'm going to just put beta 1 here and beta 2 there. And there you go. Now, that will not work, okay? That is wrong. All right, wrong. Okay, so don't do that. All right, so how do you do it? Well, there's a couple of ways you can do it, and let me show you the long way first, which kind of it's all the steps are explicit, okay? And then I'll show you a shorter way to do it, okay? So first, this one, let's answer the question. It says let's whoops, let me just scroll down a bit. Let's actually convert the above numbers into decibels, okay? And this I naught, I should explain that I naught in the formula. It's a reference intensity, okay? And it might seem strange. It doesn't matter what that reference intensity is, as long as you stick with the same reference intensity throughout the whole problem. Okay. Generally speaking, though, when we're talking about sound, the reference intensity is this number right here, and that's 10 to the minus 12 watts per meter squared. That's a very small number. That is the quietest possible sound that we can hear. Okay, it's the quietest possible sound we can hear. And all right, so let's answer the question. So what express the above intensity? So the first intensity, let's express this one right here. Where is it here? This one. Actually, let's go up a bit. This one right here. It's the same number, but already converted to MKS. Okay. So I just wanted this piece in here because that's the milli. Okay, so let's just express that in terms of decibels, and so it's this formula here. All right, and now for I, we're going to put in this number right there, MKS, and for I naught, we're going to put in that number right there. Okay, MKS. All right, and just calculate it. Okay, so what is that? Put that into my calculator and see what we get here. Oh, it doesn't like that log written out. Okay, 1 second. And it doesn't like a few things here. There we go. So it turns out to be this number here, decibels, but rounding off, I'm going to round off just to 3 decimals. 3 decimals. That's going to be 84 decibels, like that. Okay, so there you go. That's what that intensity is in decibels. Okay, so 0.25 milliwatts per meter squared is 84 decibels. Okay, and then the other one, all right, was same formula. Okay, but now it's not that number, it's this other number right here. Okay, that's that number right there, and I need the times 10 to the minus 3. Okay, so I might have gone a little bit faster. Let me just repeat what I did there. So I wanted to express both of these like that, and so that number is equal to, remember, milli isn't MKS, so it's going to be that number there multiplied by the 10 to the minus 3 piece, okay? Because that 10 to the minus 3, that is the milli, okay? And then watts per meter squared, like that, all right? Okay, so it's this number here that went in there, all right? And let me calculate this. What's this equal to? And it's going to complain about a few pieces here. All right. This one turns out to be equal to 74.4 decibels. Whoops. Okay. Now, that answers the question, but let's compare them. You know, that's like your I1. Your I1. It's not equal to that, but that gave rise to 84 decibels. Okay. And I2, which you expect to be 1/9, turned out to be 74.4 decibels. Okay, you could see already that if you take 84 and divide it by 9, you're not going to get 74.4. Okay, so that's why direct arithmetic doesn't work with beta. All right? Let me just see if there's any questions in the chat, and then I'm going to show you how to solve these same problems. But like I did on the assignment, rather than giving you intensities, what if I gave you betas and then changed the distance on you? How would you do it? Okay, so let me see if there's any questions in the chat first. Uh, a comment about my intro music. Yeah, I had to use music which was in the public domain, so it's not the best music, but it's all right, I guess, for my intro music. Okay, there are no questions, so let me go on. Now, suppose I said something like this. Let's look at the first question again here, like that. And no, actually, I mean the second question. Okay. So suppose I had this, a sound source has intensity this. What is the intensity at 30 meters? Okay, and let me scroll down so you can see it, all right? So this is a modified version of question number 2. At a distance of, well, no, actually, this is question number 2. Okay, at a distance of 10 meters, a sound source has that. But what if instead of the giving this to you in I, what if I gave it to you in beta? So, instead of this number there, I say, well, you know what? I'm just going to give you 84 decibels. You go, oh, wow, how do I do this? Because now it's an inverse R squared law. Okay, so you have to use this formula. You have to use this formula right here. Okay. Oh, it didn't cut and paste. How come? All right, let's try that again. You have to use this formula right here. All right, there we go. But I gave you, oops, scroll down. I gave you beta, and this formula is in terms of I's. So how do you do it? Well, there's 2 approaches. Okay, the first approach is, I won't actually go through it in detail. You basically, if I give you beta, all right, you would just go to this formula here and say, okay, well, I gave you beta. Beta is 84. And you know that I naught is 10 to the minus 12. Okay, and then what? Well, now you solve for I. I guess I will go through it in detail because some people might not know how to deal with the log. Okay, so you need to get I. Okay, so you see what I did? Let me do that again. Try not to go too fast. I start off with this formula. I say, well, I know I have to use the inverse R squared law, but the inverse R squared law has I's in there, and you gave me beta, so I have to turn a beta into I. Okay, think of this formula as like a conversion formula. It switches beta to I and I to beta. All right, and again, the I naught is just a constant. All right, so I give you beta, you got to convert it to I. All right, well, I plugged in for beta, I plugged in for I, and now what? Well, there's a 10 in front, so divide both sides by 10. So this is going to become 8.4, like that. And then you have to exponentiate both sides. So not 8.4, but 10 to the exponent 8.4 is going to equal, and the exponentiation undoes the log. They're inverse functions of one another. Okay, just like the tangent and inverse tangent are inverse functions, log and exponentiation are inverse functions. So like 10 to the, I'll do it on the side here, 10 to the, if you have that a is equal to log b, oh, I can't type, there we go, then you can write on the next line 10 to the exponent a is equal to b. Okay, so you see what I did there? On this side I exponentiated, so not a but 10 to the a, and on this side it would be 10 to the log b, but 10 and log, they kind of undo one another, and you just get b by itself. Okay, and that's what I did here. So instead of 8.4, 10 to the 8.4, and then here instead of the log goes away because the exponentiation inverts it. Okay, and so what is this number? Well, I can do that very quickly on the calculator. And it's a huge number, but there it is. Okay, and that's going to equal, whoops, that's going to equal this, and then multiply both sides by 10 to the minus 12, like that, and whoops, I need a multiplication in there, and that'll give you I. And you should know what I is already. It's going to be that Um, one sec. It's going to be this number. Ta-da! Watts per meter squared. Okay. All right. So you could go through all of this. Okay. And then now you've got I1, and now you're back to problem number one, because then you've got this and you've got that and that, and then you can solve for that. Okay. And then once you get I2, if I want the answer in terms of beta, well, then you got to undo this. Instead of having beta and calculating I, now you have I and you calculate beta. Okay. That's a long way of doing this. All right. And if there are no questions with that, let me show you a slightly better way of doing this. Okay, let's take this here, and let me remind you, let's just calculate this side right here. Okay, R2 was 30 meters. Okay, and R1, actually, you know what, let me, because we're solving for I2. Okay, so we have this, we're solving for I2, so let me rearrange it first. It'll make it a little easier. And so I already did that. Okay, where did I do that? I did that up here, where I rearranged it for I2. Okay, so from there to there, there's just some algebra, but I did that algebra already. Okay, now what's that going to equal? Let me just leave I1 alone. So I have I2 is equal to I1, and then over here I have this fraction, and for R1 I'm going to put in 10, and for R2 I'm going to put in 30. Okay, and let me rewrite that. Okay, get rid of the intermediate step there, like that. And what's this going to say? Well, what's this going to give you? Well, 10 squared divided by 30 squared is 1/9. Okay, and so this is equal to that times 1/9, like that. All right. So, or actually, you know what? It looks better if I put the fraction in front. Not that it makes that much of a difference. It just looks a little bit better. Okay. So, what does this say? Well, you have I1 at 10 meters. At 30 meters, you're going to have I2, which is 1/9 of I1. Okay. And you say, well, now, so what? Well, suppose we go back to this formula here. All right. And we have this formula like beta 1 is equal to I1, like that. Okay. And we can also write beta 2 is equal to I2, like that. Okay. Now, beta 1 I already gave you. That was that 84 decibels. Right? Why? Where's this coming from right there? Okay. So if you look up above, when we converted, we said, oh, I1 is like 84 decibels and I2 is 74.4. Okay. So we know that I1 is 84 decibels. And in fact, that's the way I asked the question. At a distance of 10 meters, your sound source has an intensity of 84 decibels. So this beta 1, that's at R1. Okay, good so far? So I don't want to be mysterious. I mean, you say, well, what are you solving for? Nothing yet. Don't worry about it. You just know that beta 1, that's at R1, and we know that it's 84. Okay. You can also express it by definition of what beta 1 is in terms of that. This is where all the action is going to happen. Okay. So there's the formula, beta 2 and I2. You know, there's a conversion between the two. All right. And so now you have beta 2 is equal to this. And instead of I2 here, I'm going to put in 1/9 of I1 divided by I naught, like that. Okay, so does everyone see what I did here? What I did was I took I2 out and I simply replaced it with 1/9 of I1. All right, you say, well, why did you do that? Well, because there's another property of the log, which is a very nice property of the log, and it's this. If you have log of A times B, that's equal to log of A plus the log of B. Okay, I don't know what the name of this property is. Okay, but basically what it does is it takes multiplication, the log kind of distributes over the multiplication, and it turns the multiplication into addition. So between there, you know, like maybe I should write out the multiplication explicitly. So if you've got inside of the log, you've got multiplication, that becomes addition outside of the log. Okay, and you say, well, how do I use that over here? All right, well, here's how. Okay, so you've got beta 2, and there's that 10. That 10 is just out in front, so I'm going to put square brackets here like this. Those square brackets basically is all of this. Okay, there you go. You say, well, now what? Well, take this here and pretend that's like your A, and take this the 1/9, the 1/9, and pretend that's your A, and take the I over I naught and pretend that's like your B. So I'm actually going to just put round brackets around this like this. Okay, and so think of the 1/9 there as like your A, and that like your B. Okay, you say, well, now what? Well, what does it do? See, the multiplication here gets turned into addition. So this becomes this plus log of that. Okay, and I lost my square bracket out there, but there it is. Okay, so those square brackets, I mean, I have them way out there. That's a little bit ugly, but there we go. That looks a little better. Okay. Okay, so the square brackets, those square brackets are just there to remind you that that's the entire log there. I took that entire log there and I broke it up into two pieces. Okay, the 10 is multiplying both of these. Okay, so the next line you could just get rid of the square brackets and say, okay, that's going to be 10 times this. So it's going to be 10 times the log of 1/9 plus 10 times the log of I1 divided by I naught, like that. And now you go, oh, wait a sec. I know what 10 log of I1 plus I naught is. That by definition is your beta 1. Okay, so in the next line, that is your beta 1. Like that. Okay, just by identification. In other words, there's no computation. You just look at that and go, oh, I recognize that. I recognize that as beta 1. But you know how big beta 1 is. Beta 1 is going to be 84, like that. Okay, and then you go, oh, wait a sec, I can calculate this on my calculator. And so you bring up your calculator and you calculate that, and it turns out to be this. So beta 2 is equal to that plus 84. And guess what that's equal to? Just to verify it, 74.45, like that, which rounds off to 74.5, like that, decibels. Is that what you expected? Is that what you expected for beta 2? Yeah, doing it the other way, we had 74.4. Well, 74.4 here and 74.5 there, that's a round off error. Okay, so there you go. Okay, so I did a lot there, and I hope you followed every step. Let me just very quickly repeat that second approach, okay? Because it is the better way to do it. You take a look at this, okay? You start there. You say, well, let me isolate I2, and you can even memorize the formula this way because there really are equivalent formulas like that. Okay, and then you go ahead and plug in for your R's, and this gives you that I2 is equal to 1/9 times I1, and then you go, oh, wait a sec, all I have to do is really calculate 10 log of 1/9, and you go, well, that's equal to this number here because I just did it. Okay, and then you go, okay, well, if I1 has decibels, what was it, 84. Oh no, I can't, I lost my cursor. Hold on a sec. There we go. If that's 84 like that, okay, decibels, and then I2 is going to equal the 84 decibels minus that, okay, and that's going to give you the 74.5 decibels. Okay, so that's obviously a much easier way to do it. Okay, and again, you go, well, what did you just do right here? Well, just remember, I implicitly made use of this property of the log. Okay, where I broke it up. So you can't add the 1/9 to it, or you can't multiply by 1/9. But what you can do is you can add 10 log of 1/9, okay, to the 84. So the I1 gave a beta 1 equal to 84 decibels, like that. Okay, and you go, okay, well, what's I2 then? Well, I2 is beta 1, whoops, beta 1 plus 10 log of 1/9, like that, and 10 log of 1/9 is this number there, and beta 1 is 84, so 84 minus that gives you that right there. Okay, and there's your answer. So this is the way I do it in my head. Like I don't convert from I to beta, or beta I, and then use the inverse R squared and then back. I just say, well, what factor is that R? The R's, okay, the R1 squared to R2 squared, okay, what factor is that? Is it 1/9? Okay, well then I want to take my original decibels and add 10 log of 1/9 to it, and that'll give me the new decibels. Okay, so that's the easiest way to do these problems. All right, and I didn't just do it. All that stuff that I did earlier was to show you why it actually works. Okay, and well, there it is. Okay, so I hope that helps with questions number 5 and 6. Okay, and so I already said that. All right. Okay, so if that still wasn't clear, I've got question number 4, which actually brings this out even more. Okay, and I don't think I did increasing by factors of 5. I think I did increasing by factors of 2 and 10 in the pre-recorded lecture. So I'm going to do increasing by factors of 5. Okay, this time. So let's see what happens here. Okay, so here's a new question now. So if the intensity of one bell, or actually let me call it an alarm, because decibels, bells, it gets confusing. Let's just call it an alarm, okay, or a horn or whatever, okay, some sound making machine. If the intensity of one alarm is 33 decibels at some distance, the distance doesn't matter, but we're at some distance and we're going to stay at that distance. So one alarm has 33 decibels intensity. What is the intensity of 5 of them? Okay. What is the intensity of 25 of them? What about 125? And you go, what's the pattern here? Well, 1, then you go to 5, then you go to 25, then 125. Each time you're multiplying by 5, you're going up by a factor of 5. Okay, so let's take a look at how to do that. All right, so over here, you could start off with this, and you can say, look, the intensity of 1, we'll call it beta 1, is going to be 10 log the intensity of 1 divided by I naught. Okay, and there isn't a good word for it. We tend to call that intensity and that intensity, but this is the intensity. I is the intensity of the linear quantity, and beta is the intensity in decibels. Okay, so, and they're related by the log here, like that. Okay, and you say, well, what's that equal to? Well, I tell you what that's equal to. It's the intensity of one alarm. That's equal to 33 decibels. Okay, whoops, like that. All right. And I haven't answered anything yet. Okay, I just started off with the one alarm at that. Okay, but in this form here, like that. Well, what if I had 5 of them? Okay, so let's take this formula again. And now let's say, okay, well, let's call that beta 5, because there's 5 of them. Okay, that's going to be I5. Okay, let's like that. And you say, well, what's the relationship between I5 and I1? Okay, what's the relationship in there? Well, it's obvious. I tell you what it is. It's 5 of them. So there's going to be 5 of these. So I5 is 5 I1s. Okay, the betas don't work that way where you can multiply, but the I's do. Okay, so if you've got like one I and then you've got another one, well, then just add that in and then add that in. So the I's just add. So if you've got 5 of them, you just multiply by 5. Okay, so 5I, the intensity of 5 alarms, is 5 times the intensity of one alarm. That's what this says. Okay, so in English, the intensity of 5 alarms is 5 times the intensity of one alarm. Okay, you say, well, what do I do with that? Well, in this formula here, okay, that I5, just replace it with 5I, like that. I1, sorry, like that. Okay, and now what? Well, we're going to do the same thing we did above. Let me just put round brackets around that, okay? And you can see that I'm going to use this property where I have 5 times that. Okay, so this is like the log A times B. That's like this property. Where is it? Right here. Okay, I'm going to use that property right there. Okay, log of A times B is equal to log of A plus log of B. Okay, I'm going to use that right here. All right, so how does that work? Well, I have that is equal to 5. So beta 5 is equal to 10 times the log of the first one, which is just the log of 5. That's that one right there. Plus, and I guess I got to put those square brackets in there because we're going to be distributing, or we're going to have to multiply both terms by 10. Okay, like that. All right. So this piece here is just that piece there. Okay. So log of 5 times I1 over I naught is log of 5 plus log of I1 over I naught. Okay. And now distribute the 10 over both of them. Okay. So now you've got that that's equal to 10, what's 10 times, well, 10 times the first one plus 10 times the second term, like that. Okay. And now what? Well, you take a look at this and you go, I remember that. There it is right there. So this piece is just that piece right there. And we know what that's equal to. That's equal to beta 1. And I can write it out here, beta 1. All right. And we know what beta 1 is equal to. It is equal to 33 decibels. Okay. And so now, if you take this and you work out what 10 log 5 is on your calculator, I think it's 7. Yeah, it's very close to 7. It's actually, well, I'll write it all out, but there it is with lots of decimals, but it's like really close to 7, okay? Might as well just round that off to 7 decibels. So beta 5 is equal to 7 decibels plus 33 decibels, and that is equal to 40 decibels, okay? So 5 alarms has intensity 40 dB. Okay. See if there's any questions in the chat there. Nope, no questions. All right, let me continue here. And what was next? Well, next I said 25. Okay. Well, you play the same trick again. Okay. So you start with like this formula right here, but now, whoa, it didn't cut and paste again. Let's try one more time. There we go. But now it's going to be 25 of these and 25 of those. Okay. And the intensity of 25 alarms is just 5 times the intensity of 1 alarm. That's going to be 25 times the intensity of 1 alarm. And let me group these together like this. And now what? Play the little log trick, and now I'm going to go a little faster. I'm going to have 10 log of 25 plus 10 log of I1 divided by I naught. And then you go, wait a sec, I know what this is equal to. That's your beta 1, which is 33 decibels. Like that. And then you just work this out in your calculator, and I know the answer is 14. You see, how did you know that the answer was 14? Here, I'll give you all the digits. Well, I don't know all the digits. I'll give you more digits, okay? It's very close to 14, okay? All right, so rounding that off in the next line, that would be like 14 plus 33 decibels, and that's equal to 47 decibels, like that. Okay. All right, so now what? Well, the next one was 125, so it's the same approach again. And you know what? I mean, you can just you can start skipping steps pretty quickly, because you start off with this one. Put a space in there. 125 and 125. That's going to equal this. Whoops, let's do this one here. That's going to equal that. Okay, but 125 there, and that's going to be 125. So the intensity of 125, the intensity of 125 alarms is 125 times the intensity of 1 alarm. Okay, and that's just going to reduce down to this. Okay, 125, 125, and that's going to equal this. And you know what? Without even using my calculator, I know that that number is 21. Okay, plus the 33 decibels. Okay, you go, how in the world did I know that that was 21? Well, you're going to see a pattern in just 1 second. Okay, and so let me finish. This is going to be 54 decibels, like that. All right, so there you go. All right, now, how did I know that that was 21? Well, let me show you how. If you go back up here, we had that 10 log 5 was about 7. You could just work it out in your calculator. It's a little less than 7, but that's close enough. Well, what about the next one? The next one was 10 log 25. But 10 log 25 is equal to 10 log of 5 times 5, and that's equal to 10 log 5 plus 10 times the log of 5. You go, what did you just do there? I played that same trick again where I took that multiplication and I turned it into addition. But what's that now? That is going to equal, the first one is 7, the second one is 7, and that's equal to 14. Okay, and then you do it again for the 125. And you say, well, what's 125? That's 10 times the log of 5 times 5 times 5. So that's going to be, the first 5 will give you 10 log 5. I'll just write it out. 10 log 5 plus 10 log 5 plus 10 log 5. And each 10 log 5 is equal to 7. And so this thing is going to equal 7 plus 7 plus 7, which is 21, like that. Okay, and so you can see what the pattern here is, that if you have one alarm, that was 33 decibels. If you have 5 alarms, that's going to be 33 plus 7 decibels. If you have, 25 alarms, that's going to be 33 plus 7 decibels. If you have 125 alarms, that's going to be 33 plus 7 plus 7 plus 7 decibels. Okay, so every time you increase by a factor of 25, you increase that one by 7. So what's the next one? Well, I guess it would be 625, right? What's 625? 625 is 5 times 125. Okay, and what's it going to be over here? What's going to be 33 plus 7 plus 7 plus 7 plus another 7. Every time you increase by a factor of 5, so increasing by a factor of 5, that means you multiply by 5. Every time you multiply by 5, the decibels, you add 7 decibels. Okay, so that's the pattern you should be seeing. Okay, and in this problem, I went up by factors of 5, 25, 125. In the pre-recorded lecture, I went up by factors of 2, factors of 10. It works this way with all factors. Okay, they don't all round off to nice numbers. Okay, so 10 log 5 rounds off to very close to 7. But if you did another one, like, I don't know, let's say you did by factors of 7, 10 log 7 is not a nice rounded, doesn't round off nicely. Okay, 10 log 7 is like 8.45. Okay, but it's still the same pattern. In other words, every time you increase by a factor of 7, you would add 8.45 decibels. Okay, so let me say that again. Every time you increase by a factor of 7, it would be like adding 8.45 decibels. Okay, so there you go. There's the pattern. All right, and last thing before I move on, notice this is multiplication on this side. So every time you're increasing by a factor, the word factor means it's synonymous with multiplication. So every time you go up by a factor of 5, in other words, you multiply by 5, on this side you add 7. And you go multiplying on this side and adding on this side. What's going on there? It's this. Log of A times B, all right, is equal to log of A plus log of B. And so what the log is doing is it's converting multiplication in terms of I into addition in terms of beta. Okay, and why create such a complicated scale? Like Like, why in the world did anyone ever dream up of this decibel scale? Because it just allows you, like as you start to go to larger and larger numbers here, this number on this side stays kind of relatively small. Okay, so it was just a way of making squishing a bunch of small numbers and large numbers onto the same scale. Okay, and I introduced it here in terms of sound, but it's also in like in chemistry for pH. It's all like log scales are all over the place. Okay, so if this is the first time you're seeing one, then learn it well, because you'll see it again in other things. Even if you're in like in ESS or PT, there are log scales there too. Okay, all right. And log scales, they don't work like the linear scales. All right. The last thing we did in sound was the Doppler effect. Okay. And with the Doppler effect, it's a simple formula, but there's one little kind of tricky thing in it. And it's the plus choices of pluses and minuses, and minuses and pluses. And go, well, which one do you want? Because there's, when I write plus and minus there, or so minus plus there and plus minus there, you say, well, how do I choose which one's which? Okay, and I guess the other tricky thing is VR, VS, and V. So V is the speed of whatever the wave is. In our case, it's going to be sound. VR is the velocity of the receiver. That's who's hearing the sound. Okay, like the human ear or some instrument. And VS is the velocity of the source of the sound. That's like the alarm or the horn or whatever is creating the sound. Okay, so I'll show you how to choose the signs by going through the form, going through this questionnaire. Okay, so when standing still, okay, a horn gives off a note of 261 hertz. Okay, so if you've just got this horn and it's just sitting there in front of you and it's blaring, it's going to give off a note. Okay, and that's that note is 261 hertz. Okay, I think that's middle C, by the way. All right, on the music scale. Okay, and okay, well, that's the situation. Okay, and the first question is, if the horn approaches you at a speed of 100 meters per second. Now, 100 meters per second is pretty fast, but we could do that. So this horn is actually, you're standing still. So let me read it again. If the horn approaches you at a speed of 100 meters per second while you're standing still, what frequency do you hear? So you're standing still, and this horn is approaching you. All right, so let's determine what all the velocities are. So the first one is, well, I guess let's determine the fundamental the frequency f naught. So in this formula here, that f naught, that's the frequency that you would hear if nothing's moving. That's the 261 hertz. Okay, so if the receiver and the source are standing still, then you would detect 261 hertz. Okay, so that's what that f naught is. Okay, the v in this formula here, there's the v there and the v there. That's the velocity of the wave, and in our case, it's sound 340 meters per second. Okay. All right. Now what? Well, there is the velocity of the source and the velocity of the receiver. Okay. So the source is what's ever producing the sound. What's producing the sound? Well, the horn is. Okay. And so the horn, it's moving at 100 meters per second. So the velocity of the source is going to be 100 meters per second. Okay. Like that. And the receiver is you. Okay. And you are standing still. Okay. So I say here, while you're standing still, what frequency do you hear? So you, the receiver, are VR equals 0 meters per second, like that. Okay. And there you go. There are all the pieces. You say, okay, great, let's plug into this. Except that as soon as you do, you go, uh-oh, I've got these pluses and minuses all over the place. What am I going to do with them? Well, first, let's plug in the numbers and see that one of the choices will go away. So for that f naught there, that is going to be 261 hertz. Okay, so for f naught, we replaced in that 261 hertz. Okay, so for the v here, that's the velocity of the sound. That's both. We put some spaces in there so you could see it. Okay, that v there, that's the speed of sound. So that's 340 there, and it's both in the numerator and in the denominator, like that. Okay, great. And VR here, that's 0. Okay, and VS here, that's 100. Okay, and you'll notice that right here, you've got 340 minus or plus 0, okay? So that's a choice. You could either do 340 minus 0 or 340 plus 0, but you realize that whether you're adding or subtracting 0, it doesn't matter. So for this particular problem, not always, but in this particular problem, that plus minus doesn't matter because that goes away, okay, like that, all right? So because the receiver isn't moving, it doesn't matter whether you add or subtract that, okay? It's the bottom one that matters, okay? And now the way I do this in my mind is I just say, look, do I expect the frequency to go up or go down? And with the Doppler effect, if the two are approaching one another, it doesn't matter whether one is whether it's the receiver or the source that it's approaching, or if they're both approaching or whatever, as long as the distance between the two is shrinking over time. Okay, so one is approaching the other, or they're both approaching one another, so the distance is decreasing over time, the frequency will go up. Just remember that. Okay, so the frequency goes up when things are approaching. All right. Now, if you choose the plus here, so you got a plus or minus in the denominator. So here's the denominator, and you could say it's going to either be 340 plus or 340 minus 100. You go, well, which one do you want? Well, if you choose the plus, your frequency will go down. Okay, try it. And so you go, oh, well, that's wrong. Physically, that's not what happens. What happens is the frequency has to go up, and so you must choose the negative. Okay, and that's the way I remember it. It's the easiest way to remember it, okay? Again, I just say, look, the two are approaching one another, and the frequency must go up, and therefore I must choose a minus, because if I choose the plus, it'll go down, okay? And so let me plug this into my calculator and see what that gives me. That gives me this frequency right here, all right? It equals that, all right? Hertz. And I guess we should round that off. That's going to be F is equal to 370 hertz, like that. Okay. And does it always ask, does it make physical sense? Okay. Well, when it's standing still, it's 261. When it's approaching you, it should go up. So it's 370. Okay. And that's quite a shift. That's a shift of, like, roughly 109 hertz. Okay, so that's quite a shift, but that's because this thing is traveling at 100 meters per second, which is about a third the speed of sound. So this thing it's really moving towards you. Okay, and well, there you go. All right, so all right, now for question B, I kind of turned it around. I said, okay, if you approach the horn at 100 meters per second while the horn is standing still, what frequency do you hear? Okay, so you have to think here. Who's the receiver? Well, you are, and you're approaching. So out of these numbers here, let me just cut and paste them like these, like that, okay? Out of these, that stays the same, right? Because that's just the frequency of that the horn emits when it's standing still. It's the base frequency, if you want to call it that. This one stays the same because it is the speed of sound, okay, and that's 340 meters per second in air. And now here you have to say, okay, well, what do I want there? Okay, now the horn, whoops, let me scroll down a bit more. The horn is the thing that is the source, and the horn is standing still. So the source is standing still, and so it has a velocity of 0. Okay, and the receiver, that's you, and you are approaching at 100 meters per second. So now VR is equal to 100 meters per second. There you go. Okay, so you'll notice that the difference between this part B and part A is that these two, the source and receiver, have switched values. Okay, and let's take this formula here, right there, and let's plug in. So now we have, let me just grab this piece from here like that. Well, no, let me not, because I don't want to confuse you. Go one step at a time. So for F naught, that's 256. Then we have this piece right here. For the V's, let me put some spaces in there. For the V's, we have 340 and 340. And for VS, that's the source. The source isn't moving this time, so VS is 0. And so now we don't have to worry about the plus or minus 0, because if you add 0, you subtract 0, it doesn't change anything. Okay, so there we go. The denominator is fine. Here we have 100, And we have to decide, do we subtract or do we add? If we subtract, the frequency will go down. If we add, the frequency will go up. And you say, okay, well, are they approaching or are they receding from one another? And they are approaching, okay? Again, for the decision of the plus minus, it doesn't matter which one's really moving, okay? And so the frequency has to go up, okay? And so over here you go, oh, well, if the frequency has to go up, then that has to be a plus, okay? And let me work that out. And that turns out to be this number. Hertz. And rounding off, it's going to be 338 hertz, like that. Okay, so is that what you expected? Yeah, you expected it to go up. So it starts off at 256, and now you're hearing 338. Okay, notice it's not symmetrical. It does matter whether it's the source that's moving towards the receiver or the receiver moving towards the source. When it's the source moving towards the receiver, we got 370. So that was the source. The horn was moving towards you and you're standing still. However, if the source is standing still, that is the horn standing still, and you approach 8, it's less. It's 338. Okay, so 370 compared to 338. All right. So there you go. The Doppler effect in the air is asymmetrical that way. The Doppler effect for light, which also happens for light, is symmetrical because of the special theory of relativity. Okay, we're not going to do that, but I'm only mentioning it because if anyone takes the astronomy course, there you will look at the Doppler effect applied to light, and you might go, well, why is it a different formula? Well, because when it comes to things traveling at the speed of light, you have to use the relativistic versions of the formulas, and there they are, symmetrical. Okay, so that's just a bit of an aside, but again, for anyone that might take an astronomy course, and you will definitely study Doppler shift of light in an astronomy course, you would see a different formula. But this is the formula we're going to use for us because we're more interested in the Doppler effect for sound. Okay, and then the last question is what frequency do you hear if you both approach one another? Okay, now if you're both approaching, both of them want to increase the frequency. Okay, and so in the numerator you're going to choose the plus because that'll increase it. In the denominator you're going to choose the minus because that'll increase it. Okay, and so now your numbers will look like this. All right, the source is traveling at 100 meters per second, but so is the receiver. Okay, let me read the question again just so we can see why. What frequency do you hear if both you and the horn travel away? I apologize. I read the question wrong. I'm glad I reread it. You're both traveling away. Okay, so I put a little twist to this one. If you're both traveling away from one another, both of them want to decrease the frequency. Okay, so this time to decrease it in the numerator, you're going to choose a minus, and to decrease it in the denominator, you're going to choose a plus. Okay, and just try it on your calculator and you'll see what happens. But they're both traveling at 100 meters per second, but they're traveling away. So starting with this formula right here, okay, what are you going to do? Well, the base frequency here is 261. Okay, the velocity of sound is 340 meters per second and 340 meters per second. Okay, and the receiver is traveling at 100 meters per second, and the horn is traveling at 100 meters per second, and both of these are trying to raise the frequency. Okay, and so you say, okay, well, if I choose a negative here, well, that makes a smaller denominator. Numerator. If I choose a negative there, you get a smaller numerator, and a smaller numerator means a smaller f. And so no, it's got to. I'm sorry, I said it the wrong way, didn't I? We do want to choose the negative because we do want a smaller, because they're moving away from one another. So if they're moving away from one another, the frequency has to drop, and in the numerator, to get them to drop, we choose the negative sign. Okay, so there we go. So that's going to make it drop in the numerator. In the denominator, okay, we want to divide by a bigger number, not a smaller number, to get an even bigger drop, and so we want the plus. Okay, All right. And again, I kept confusing this in my mind. They're both traveling away from one another. So they're both trying to decrease the frequency. When things travel away, they decrease the frequency. And so both are trying to decrease the frequency, both the receiver and the source. For the receiver to decrease the frequency, you want a negative in the numerator. For the source to decrease the frequency, you want a plus in the denominator. Okay, so that's how I think it out. All right. By the way, part C is about as complicated as you can get with these problems. All right, and what's that going to equal? That's going to equal this number right here, hertz. Okay, or rounding off, that's going to be 142 hertz, like that. Okay, and is that a decrease? Well, yeah. 261 drops to 142 hertz. Okay, and so there you go. There's the Doppler effect. All right. Let me see if there's any questions in the chat here. And it doesn't seem like there's any questions. And we've pretty much covered everything with sound. I went a little bit slower this time through, and that's because I wanted to go over the whole decibel thing a little bit more carefully. I could see why questions 5 and 6 were a little bit difficult, but these log scales are important. So, make some effort to learn them. You will see them again in other courses. All right, last chance to ask any questions. Otherwise, we're done for the evening. Okay. Just wait a few seconds. There's 3 people in the chat. All right. So I assume everyone will watch this tomorrow morning or tomorrow during the day. All right, it doesn't look like there's any questions. I'm just going to say goodbye to everyone. Goodbye, everyone. All right. Bye-bye. Ending the chat.